Hi guys, imagine you are trying to predict tomorrow's inflation rate, or next month interest rate, or the trend rate next quarter. Should you fit a trend line through history? Sometimes, but here what a professional economist and quantitative analyst know. Many financial variables don't simply move upward over time. Instead, they remember where they came from. Yesterday influenced today. Today influenced tomorrow. The idea is the foundations of one of the most important time series models in finance, the autoregressive model or AR model. In these lessons, we will learn how AR model work, why covariance stationary is essential, how analysts forecast future value and what mean reversions really means, and how professionals evaluate whether an AR model can actually be trusted. So in the previous lessons, we learned how trend model describe long-run movement over time, but financial markets rarely involve based only on time. Think about inflations. If inflations were high last month, it's unlikely to suddenly collapse to zero next month. Interest rates behave similarly. Exchange rate, bond yield, economic growth, all of these tend to exhibit persistence. In other words, today depends partly on yesterday. This is where trend models become limited. They explain movement over time, but they ignore the influence of the previous observations. Professional forecasters saw this, allowing the variable to predict itself. That idea leads us directly to the autoregression model. So, the word autoregressive sounds complicated, but the intuition is actually simple. Auto means self. So an autoregressive model is simply a regression where a variable is explained by its own past value. The simplest version is called an AR1 model. The equations is t equal b0 plus b1 is t minus 1 plus epsilon t. Let's unpack it. Today, values depend on three things. First, a baseline level represented by the intercept. Second, yesterday value, and third, a random shocks. Notice something important. Time itself is no longer the explanatory variable. Instead, history became the predictor. That's why AR models often outperform simple trend model when forecasting financial and economic data. The number inside the parentheses tell us how many lag observations the model used. An AR1 model looks back one period. An AR2 model uses the previous two observations. More generally, an ARP model includes the last p value. Think of it like memory. AR1 model has a short memory, and AR5 model remember the last 5 periods. Choosing the appropriate lag length is one of the most important modeling decisions because including too few lag ignore useful information, while including too many can make the model unnecessarily complex and stable. Before an AR model can be trusted, the time series should be covariance stationary. Why? Because almost every statistical inference behind OLS regressions assumes the data behave consistently over time. A covariant stationary series satisfies three conditions. First, its expected value or mean remain constant. The average level does not drift upward or downward indefinitely. Second, its variance is constant. The degree of fluctuation around the mean remains stable. The series should not suddenly become dramatically more volatile. Third, the covariance between observations separated by a given lag remains constant. For example, the relationship between today's value and yesterday's value should be similar regardless of whether we are looking at observations from 5 years ago or last month. These three properties create stable statistical environments. Without them, the model estimate relationship may not remain reliable. Let's examine what happens when these conditions fail. Suppose the average level keeps rising every year. Now the mean is changing over time, or image market volatility doubled during a financial crisis. Now and the variance is changing. Or perhaps the relationship between today's observation and yesterday's observation changed dramatically after a major policy shift. Now the covariance is unstable. In each case, the statistical assumptions behind the AR model begin to break down. This makes forecasting much more difficult. One of the biggest challenges in financial market is that the economic regime changes. Interest rate, environment change, regulation change, investor behavior change. All of these can reduce the stability of historical relationship. Now let's see how forecasting actually works. Suppose we estimate an AR1 model. Forecasting one period ahead is straightforward. We simply plug today's observed value into the equations that gives us forecast for next period. But what if we need a forecast 2 periods ahead? We face a problem. The actual value for next period hasn't happened yet, so we use our old forecast. The one-step forecast becomes an input into the two-step forecast. This is called the chain rule of forecasting. Each new forecast depends on the previous forecast. Here's the important implications. As we move further into the future, forecast uncertainties increase. Errors accumulate over time. That's why long-term forecasts are almost always less reliable than short-term forecasts. Building a model is only half the job. The next question is whether the model has captured all important patterns. To answer that, analysts estimate residual. Residual represent the predictions error. If those errors still display autocorrelations, it means important information remains unexplained. The testing procedure is straightforward, estimating the AR model, calculating the autocorrelation of the residual. When test whether that autocorrelation is statistically different from zero, ideally the residual should resemble random noise. If significant autocorrelation remains, the model is incomplete. Perhaps an additional lag should be included instead of an AR1 or AR2 or AR3. Model may be capture the dynamic of the data. The objective is simple. Keep improving the specifications until the residuals no longer contain systematic informations. One of the most fascinating properties of many financial variables is mean reversions. Think about interest rate. They may rise above their long-run average, but they rarely continue rising forever. Eventually, they tend to move back toward a normal level. The same idea often applies to exchange rate, valuation multiple, credit spread, and commodity price. An AR1 model naturally captures this behavior. Its long equilibrium is B0 over 1 minus B1. This is called the mean reverting level. If the current value is above this level, the model predicts a decline. If the current value is below it, the model predicts an increase. In other words, the series tends to pull itself back toward equilibriums. A model can appear excellent on historical data and still perform poorly in the future, and that's why analysts distinguish between in-sample and out-of-sample forecasts. In-sample forecasts evaluate how well the model explains the data used to estimate it. This tells us how well the model fits histories. But investors care somewhat about the futures. Our sample forecasts evaluate predictive performance using the data the model has never seen. One of the most common evaluation metrics is the root mean square error, or RMSE. RMSE measures the typical size of forecasting error. Lower RMSE indicate greater forecasting accuracy. When comparing competing AR models, the one with the lowest outsample RMSE is generally preferred because it demonstrates stronger predictive ability on unseen data. Finally, there's an important practical issue. Financial market never stands still. Central bank change policies, government introduce new regulations, technology transform industry, consumer behavior evolve. Because the world changes, model coefficients also change. A regression estimate using 10 years of data may no longer describe today's economy accurately. There's a trade-off here. Using more historical observations improves statistical predictions, but older observations may no longer reflect current market conditions. Using fewer observations capture the current environment better, but provide less statistical information. Professional analysts constantly balance the competing objectives. Model building isn't a one-time series exercise. It's an ongoing process of updating, testing, and adapting to new economic reality.